today we've got a very cool one, and it's going to be a bit of a challenge to finish in time, but we'll see what we can do. So the matrix tree theorem. Matrix tree theorem gives us a way to figure out the number of spanning trees of any connected graph, at least. Okay, so let G be a connected graph with Laplacian matrix L of G. Let L star of G be result of removing the first row and column from L of G. Okay, so you have your Laplacian, just delete the first row and column from it to get this special L star of G. This theorem actually holds, and the proof works if you delete any row and column, like one of each. Everything works fine here. But just for the proof's sake, it's a little easier to just assume it's the first one. Yeah, okay. So then what? So then the number of spanning trees of G is just the determinant of this special like submatrix of the Laplacian. Okay, so you just create this matrix, which is really easy to do. And then you take to find the determinant of it. So if you're working with a concrete graph, like computationally, you just plug this into a computer and immediately get the number of spanning trees without much work. If you have like an abstract tree, an abstract graph, you can still work the determinant with typical linear algebra, which is exactly what we'll do, because what's Cayley's formula then going to be? Well, Cayley's formula will just ask for how many spanning trees are there of Kn, of the complete graph, right? All the spanning trees live inside the complete graph. So if we enumerate all of those, then we found all spanning trees. And what's nice is the Laplacian for the complete graph is very, very simple. Complete graph super, super uniform. Let's remind real quick what the Laplacian looks like. So the Laplacian of a graph here, it's an n by n matrix, n being the number of vertices of the graph. Along the diagonal are just the degrees. Okay, so the degree of like vi is here in the I by I column there. And then all the other entries are either -1 or 0, depending on whether the corresponding vertices are adjacent or not. So like vi, vj has a -1, sorry, in its coordinate here if there's an edge, and a 0 otherwise. So this matrix is really easy to fill in, especially for the complete graph. Right, in the complete graph, well, we'll see in a moment, but the diagonal is all n-1s. Every vertex has a degree n-1. And otherwise, every pair of vertices are adjacent, so everything else is a -1. So we want to find the determinant of a matrix that's all -1s, except for some constant value across the diagonal. Some easy row operations should get us to something we can compute right away. Okay. So Cayley's will follow immediately. We may not have time for that, but yeah. Okay, so let's do the proof here of the matrix tree theorem. So first off, we need a little bit of notation, and then we need an important theorem from linear algebra, and then we'll sort of talk graph theory. So fix integers a and b, and matrices a, that is a by b. So a is a by b, and b is b by a. Okay, matrices there. So a has a rows, b has b rows. Okay. Okay, so for a subset S among the, say, indices of B. So let me write this and then explain. And let me put this thing on. So S is a collection of column indices for A and row indices for B, say, right? It's just some list of the rows and columns. It's just a subset. Let A sub S be submatrix of A. Yeah, let's say using the columns of A indexed by S. So what do I mean by that? Let's look at it like an example here. So like A sub, say, I don't know, what's my example here? 1, 3, 4 is going to look like it's the result of the matrix here, where I take the first column, not the second column, take the third column, the fourth column, and like not the fifth. I don't know, say there's 5 columns here. Okay, does that make sense what A of S is? It just tells you which columns to keep around. Okay, and then B is whoops, I don't want that. B is defined similarly, except so and B sub S is same. I'm just going to say it's the same for rows. Okay, so it's a little bit confusing because when I talk about B sub S, I'm talking about keeping the rows. So like, let's say B sub, let me just do a different one. 1, 2, 5 is going to be the result of keeping rows 1, 2, and 5. So I keep row 1, I keep row 2, I delete 3 and 4. Okay, that's not so clear. 3 and 4, and keep 5. Okay, so if I write down like an arbitrary matrix sub S, it's not clear whether I should be taking rows or columns. Like, how do I distinguish these two? This situation is because of the B index that's appropriate here. So if you want to talk about A sub something, you need to specify the universe S is being taken from. Otherwise, this is very ambiguous. But we're only using this for this proof and on one occasion. So when we use it, it should be crystal clear. But what's important here is that this has B rows and this has B columns. So it makes sense to choose some of them, right? If I wanted to take rows of A, I should be choosing S from a subset of size 1 up to A, all right? So anyway, so yeah, just be careful. Like these AS and BS are not the same. You can make these work consistently by taking a transpose and doing all that business, but I'd rather just define it this way to avoid a bunch of notation, okay? And then, so in particular, if the size of S that we picked is of size A, then we have this nice situation that A of S and B of S are both A by A matrices, right? A has A rows anyway, and I'm keeping A columns of them if S has A elements in it, and same for B. B has A columns, and I'm keeping A rows, so I get an A by A matrix in both these cases. And actually, that's the way these ones are going to work. I'm only ever going to look at A sub S and B sub S when the size of S is A. So I'm going to try to get these nice square matrices when I apply these. Okay, and so there's this important theorem of linear algebra, the Cauchy-Binet theorem. So Cauchy-Binet, let's say formula, which I'm not going to prove. It's not very hard to prove with linear algebra, but it's sort of not the best use of time here. It tells us a strategy for computing the determinant of the product of two matrices A and B. Again, say A and B are A by B and B by A, so it makes sense to multiply them. Then what you can do is take this following sum here, where you compute these determinants, A sub S and B sub S, where S is a subset of 1 up to B, and S has size A, okay? So in each of these, you're computing determinants of a submatrix that's A by A in this guy and A by A in this guy. And you're just doing this. This is over every collection for A, every collection of A columns with all the rows. And this one's every selection of A rows of the B rows, okay? So there's so many ways to do that. In fact, there's B choose A different ways to do that, and we can compute all these, okay? Now, of course, like from a computational point of view, this doesn't seem very useful because the right-hand side looks like an awful lot of work, but we won't use it to compute anything. I mean, like with a computer when I say that. I mean, we will use it to compute something, but what's nice about it is if A and B are a little bit complicated, but S is chosen in such a way, like this value turns out that these matrices are very, very simple. When you take these sub things, they all look really nice. Then this can be computed very easily. And in fact, we'll see that choosing the appropriate A will turn these matrices into essentially like incidence matrices for some kind of subtree. Okay, so I'm just talking ahead a little bit here. But okay, so we've got Cauchy-Binet. We'll have to scroll back up to it when we apply it. But now we've got the sort of easy the easy linear algebra groundwork laid here. Okay, so now let's let G be an n vertex, m edge graph. Let's say it's connected graph. Okay, so this is the G for which we're going to try and find the number of spanning trees. Okay, and let's say with incidence matrix I of G and Laplacian matrix L of G. Okay, we recalled a moment ago what the Laplacian is. The incidence matrix, just as a reminder here, it's a very simple concept, but you have an n by m matrix, vertices by edges, and it's a 0-1 matrix, and you have a 1 if the appropriate objects are incident. So like you have, let me put it like here, you have a 1 if vi is contained in E, the corresponding EJ there. So I index the edges here, vertices here, put a 1 if they're contained, a 0 otherwise. Okay, and so as we observed, and this is important here, each column has 2 1s for the opposite ends of the edge, and each row has as many 1s as the degree of vi, because that's the number of edges that it's contained in. Okay, all right, so now I'm going to construct a matrix Q as follows. So I'm gonna modify the incidence matrix slightly to get this new matrix Q that's a little more relevant to our what we're doing here. Okay, so in each column of I of G, replace 1, 1 with -1. Okay, so remember each column has 2 1s in it. In Q, I'm just going to like randomly choose one of these 2 and turn it to a -1 and a +1 here. Okay, it's not really important. It's not important at all which way you choose this. It will help us for computational reasons, but let me try to let you visualize what's actually happening here. So we haven't talked about directed graphs too much, but remember when we talked about branching forests, we oriented the edges and we said each edge just let it go from, we said they were oriented away from the root. Well, it's very natural to record the same thing in a matrix where 1 represents the start of the edge and -1 represents the end of the edge, or vice versa. It's just marking the 2 edges. And so all this is saying is each edge of the graph like gets this kind of like orientation. And then this becomes the 1, this becomes the -1. And then if you look at like a VI here that goes across, the -1s are how many times an edge points into it, and the +1s are how many times an edge points out of it. We don't need any information about that, although this stuff will come up later, but just to have an idea what that's doing. So that's, okay, that's the first step of Q. Then remove row 1 of this matrix. Okay, so we remove the first row of I of G after doing the switching of one of the 1s to one of the -1s. Okay, so maybe this is a good sanity check for you guys. Q is, what by what is Q here? Just to make sure we're, how many rows does Q have?
Like n-1, where n is the number of vertices.
Yes, exactly, right? So the incidence matrix had n rows because we have an n vertex graph, and we removed the first row. So it has n-1. And then the number of columns is the number of edges. We didn't do anything with that. Incidence matrix has as many columns as that. Okay, so now here's a key observation that's actually a homework. I mean, it's an exercise in the book. I may not assign it as a homework, but the observation is that L star of G is equal to Q times Q transpose. Okay, so L star was this submatrix of the Laplacian where I deleted a row and column, and I'm saying that it's the result of multiplying this weird matrix Q with QT. Okay, so let me not prove that. Like I said, it's an exercise, but let's think about this for a second. If you take the incidence matrix and multiply it by its transpose, then you don't quite get the Laplacian, but you get something that looks very much like the Laplacian. Because, like, think about when you multiply these 2 matrices here, along the diagonal of the resulting graph, it's not hard to see that you get degrees. Okay, the number of 1s, these will collect up the degree of each vertex there. Okay, and then you're going to get 1s or 0s here, depending, like, so the resulting matrix when you take I by I is going to be n by n, right? So it's going to be indexed vertices by vertices, and it's going to be this matrix that's very closely related to the Laplacian. In fact, it's the Laplacian with all the 1s changed to +1s instead. Again, I'm not like proving this. I'm just trying to give you like a rough visual that this is true. And the argument for that is basically the same as this, because what's here, this Q and this QT have 1 row removed from both of them. So it makes sense when I multiply them together. If I and I gave me basically the Laplacian, then Q and QT will give me the Laplacian with the first row and column removed. And then why do I get negative ones? Well, Q and QT each have one negative one in a column, right? And one. So when I multiply them together, instead of getting ones, I'm going to get negative ones there. Okay. Like, you know, why do you get that? Well, the negative one in VIBJ becomes a positive one in sorry. Let me not put it into words. Okay. Just, this is the rough idea for why it's true. It's not hard to prove. Okay. It's just matrix multiplication. But in some sense, it is the crux of the proof, because this thing here is going to allow us to apply Cauchy-Binet. All right. Okay. In fact, that's exactly what we want. So Cauchy-Binet says, as long as m is greater than or equal to n minus 1. Remember, Cauchy-Binet, we started off with fixing b is greater than or equal to a. And these matrices here are n minus 1 by m. So m needs to be at least n minus 1. B needs to be at least a. Is this true? Does this make sense? Can we actually use this information? How do we know that m is at least n minus 1?
Because it is connected.
Very good, Christian. Yes, exactly, right? We started with G is connected, wherever it was, up here. And we know that actually that's, it's one of the things we didn't quite finish in class, although we know anyway, minimally connected graphs have n minus 1 edges. You can't have fewer than that. So we absolutely have to have the number of edges is at least n minus 1, which conveniently, the number of rows of Q is n minus 1 because we deleted one row. So we're trying to apply Cauchy-Binet to this thing here, and the numbers work out. Like A is less than or equal to B as far as that's concerned. So Cauchy-Binet then says determinant of L star G is just the determinant of Q QT. That's not Cauchy-Binet, that's just an identity, right? I'm replacing L star with Q QT. But now Cauchy-Binet applies to this guy here because I'm asking for the determinant of two matrices here. And so this sum should be, this is easy to flub here. It's going to be determinant of Q sub S times determinant of Q transpose, that's the other matrix, sub S. And then S is going to be indexed from the larger of the two values among here, so among 1 up to m. And what should be the size of S then? If you just to read out from Cauchy-Binet, it was A, and what's A here again?
N minus 1.
N minus 1, yeah, exactly. And then nicely, this actually simplifies very nicely. Can someone tell me what this simplifies to using a little bit of basic matrix theory? What can you tell me about those two determinants? You have the determinant of QS, I don't know, whatever that is, and the determinant of QS transpose.
It's the same thing.
Yeah, exactly, they're the same. So I can just take the determinant of QS squared. Okay, so now we're getting somewhere. We're simplifying things a little bit. Now we need to figure out these determinants of QS. Okay, now let's make a little observation here. So observation, yeah, if, okay, I'm going to abuse notation a little bit here, but if S is as described in the statement, so it's a subset of M of size n minus 1, then QS is, yeah, the columns of Q corresponding to a subgraph of G with, yeah, n minus 1 edges. All right, let's think for a second here. Q was just Q itself. It basically was the incidence matrix with some ones changed to negative ones. Ignore that for a moment. And then the first row was deleted. The first row corresponded to the first vertex. So we pretended that that was deleted. But the columns of Q are just, they correspond to columns of the incidence matrix. And what is a column of the incidence matrix? Like, where does that come from? It's an edge, right? The columns of the incidence matrix are edges. And so if in QS, remember, what's QS look like? It's just the preservation of the, you know, rows corresponding to the value S, the values of S. So it's saying, grab these columns here. Now there is like this hidden missing row up here that did belong to I of S, but that doesn't affect the existence of edges. Even if an edge was on V1, its other endpoint would exist in this column. So we can like backtrack a little bit and say, oh, each of these columns is an edge. okay? So each of these columns is an edge of G, actually. And how many of them are there? Well, remember, we took n minus 1 columns, right? So there's n minus 1 edges. So so QS are columns of Q, and those columns correspond to n minus 1 edges in G. And if I just say, hey, here's n minus 1 edges of G, then they span a subgraph of G, right? They just take the endpoints of them together. Those edges are a subgraph in one way or another, okay? And so our question here is going to be, do those n minus 1 edges form a tree in G, or do they not, right? They either do or they don't. If they do, then it's a spanning tree, obviously. If you take n minus 1 edges and it's a tree in a graph on n vertices, it's no choice but to be a tree. This follows from our tree properties. And so, and furthermore, every tree will be enumerated in this way, right? If I consider every single subset of n minus 1 edges, every spanning tree that exists will eventually appear because I've literally gone through the entire list. So that's what we're going to actually do here is, okay, so here's the abuse of notation. A couple of times I will refer to QS as a graph. So when I say the graph QS, I mean the subgraph of G spanned by the n minus 1 edges corresponding to Q of S. And keep in mind, this is on n vertices. Even though I deleted this row here, like there's still the edges that correspond to that. Vertex doesn't disappear from my graph just because I took it out of this like weird proto matrix that helps me out. Like it's still there, okay? But QS can also kind of be thought of a graph, and what graph? It's just this transformation from, oh, take the columns, look at the corresponding edges, look at them as a subgraph, okay? All right, so what's next here? Okay, so what are we going to show? We want to show, and this is what we will show, that if QS, I'm going to just say spans a tree, okay? So like what do I mean? Remember, Q of S corresponds to n minus 1 edges. If those n minus 1 edges form a tree, then I'm going to say that the determinant of Q of S squared equals 1. I'm going to try and prove that. And it equals 0 otherwise. Okay? That's what I want to show. And this actually proves my theorem. Let me scroll up a little bit. Why does this prove my theorem? Well, remember, this index here will check every single n minus 1 edge subgraph of G. If this creates a tree, then this sum here will contribute a 1, right? Because when QS is a tree, I get a plus 1 there. If it's not a tree, then I get a plus 0. So if I compute this whole sum, it's just the sum of a bunch of 1s, as many 1s as there are spanning trees. And so by Cauchy-Binet, that's equal to this guy here, right, on the left-hand side. And the claim of my theorem is that this counts the number of spanning trees. And so if I prove this, that's literally what this thing does. So I need to somehow check the determinant of Q of S. Why is it 1 when it's a tree, and why is it 0 when it's not a tree? I need to specify both of those, right? If I don't get the second part, then I have an upper bound on the number of trees. So I need both 1 and 0. So each time I check, it adds 1. So each tree is counted once exactly. Okay, so let's do it in 2 cases, whether QS spans a tree or not. So case 1, I think the not a tree is easier to see. Yeah, so QS is let's just say is not a tree. Okay. Okay. So since QS is not a tree, there exists a component C in Q of S. All right. Again, Q of S is, I'm talking about the graph spanned by these n minus 1 edges. There's a component in it in Q of S that does not contain vertex V1. Okay, I mean that's what it means to not be like. So if you're not a tree, oh yeah, okay, actually, so we have a component. Yeah. Okay, actually, this requires a little bit of explanation. If you're not, why are you not a tree? There's 2 possibilities, right? You're either not connected, or you have a cycle. Both of these, if you have n minus 1 edges, will correspond to just being not connected, right? This actually follows from our theorems, but either you're not connected and you're not connected, Or if you have a cycle and n-1 edges, then you're also not connected, right? We actually, that's part of the homework, I think, that one specifically. So that means that there is indeed a component that's not adjacent to vertex V1, right? I mean, V1's in a component with something, and there's some other component. So just think of it that way. And I chose V1 specifically because V1 is the vertex that we sort of like threw away when we computed Q, okay? So it doesn't exist in Q. It doesn't exist in the matrix Q. It exists in the graph Q, a QS, okay? So now, this means, let me actually draw the picture here then. This means that this is, say, Q of S, and look at rows of Q of S corresponding to vertices in the component C, okay? C doesn't contain V1, so like this missing row here doesn't come into play at all, fortunately, because it doesn't even exist in the matrix. So like, luckily it's not in C at all. So what do those rows look like? The rows look like, here's one of the rows, and here's one of the rows. In principle, it could be all of Q of S, right? Maybe my graph on n-1 edges contains all of Q of S except for V1, maybe. But let's say it has 3 for illustration purposes here. Okay, so these are the rows corresponding to the component C. Like there's some other rows that are not in it here potentially. Okay, those are other rows that are not in it. But now let's look at the columns of the columns. Let's see, how do we say this here? I only want to consider these circled columns here for a moment there and look at the submatrix spanned by those rows. Okay, so look at rows and just consider this sub matrix of QS, so spanned by the rows there, okay? In these rows, there's no edge leaving. These are vertices, right? Each of these is like V5, V9, V10, whatever. There's no edge leaving these rows because this is a component, right? It's a component of the graph. All the edges are inside of that component. Nothing goes out of it. Otherwise, that would be a larger component. So what that means is that if I look at each of the columns here, among these rows, there's going to be a 1 and a -1, because remember, these are these 1 negative ones correspond to the edge between V5 and V9. And that edge is definitely contained among the rows here, right? And then there's maybe a 1 here and a -1 here. And, you know, say V5 is also adjacent to V10. Like what I've described here is actually a triangle here, okay? I see Jose smiling, so he probably sees exactly what's going to happen here. Right? What happens if I add up all these rows together? If I add rows from C, I get, what do I get? What does that row look like if I add up all those rows together? Yeah, 0. I get a row with a bunch of zeros because like the 1 and -1 will cancel. So that's why I introduced -1s up in Q so that this could happen, so that I could get a bunch of zeros. So if I add the rows from C, I get a row of all zeros, right? So if you do row addition in a matrix and you end up with a row of all zeros, by doing that, what does that tell you about that matrix? Q of S itself, right? Or what does that mean about those rows? So
if it's not full rank, then it has determinant 0.
Yeah. So those rows, what am I trying to say? Are linearly dependent. Let's put it that way, right? They're linearly dependent. So the determinant of the full thing, QS, is 0, okay? Because that component worked together. All right. Don't forget, V1 was missing from this thing here. Okay. The component still could be everything else there, but I add them together, I get 0. QS is determinant 0 because some of the rows were linearly dependent. Okay. All right. So now let's look at case 2. And this one, it's not any harder, but say QS is a tree. Okay. So now we're going to use another property of trees. Yeah. We're going to use another property of trees. So we did this once before, and I'll write out a little bit here, but suppose you have a tree. We know there's a vertex of degree 1. After this homework, you guys will know that very, very well because this fact is repeatedly used in the problems, but it's like in a lot of ways the most important fact about a tree. It has a vertex of degree 1. if you remove that vertex of degree 1, it also destroys that unique edge that was adjacent to that vertex. And then you're left with still a tree, right? This nicely doesn't disconnect the tree. You're like pruning it. The resulting tree also has a vertex of degree 1, and you can prune it again and again and again. You can eventually get rid of all the vertices that way, where at each step you still have a tree, okay? So let's say that then there exists a vertex v1 of degree 1 with incident, I'll just say with edge because it's clear, e1. Remove and find v2 with edge e2. It's v2 with edge e2. Again, v2 is degree 1. Just keep doing this procedure and so on. To enumerate vertices as v1 up to vn and edges. Let's say we go up, we'll enumerate all the way up to vertex vn minus 1. At the end, you have one vertex, and this doesn't actually apply anymore. The vertex vn at the end has degree 0, so there's no like special edge for it anymore. And these gives you edges e1, e2, all the way up to en minus 1. Okay. Remember, QS had n minus 1 edges there, so we remove one edge at a time. Now we have to be careful here. We're talking about labeled graphs here in principle, so we have to be a little bit careful about what's going on here. These, I'm renaming the vertices here so that I have, like, if the vertices were literally, v1 up to vn minus 1, which is actually how I've referred to them before, then maybe I should rename this list as u1 up to un minus 1, and then make these f1 up to fn minus 1. I can rename them, like by changing the names of the labels so that they come in this order here. Just keep in mind, I'm not claiming I'm not giving a new labeling. I'm not guaranteeing that the vertex labeled 1 has degree 1. I'm just giving them new names so that I have this nice thing, this nice list here, right? This is a strategy actually you want to employ in homework number 6 as well, in a sense, although in a sort of simpler way. Now observe, this is the key observation here. Observe that in the way that this is oriented, that for I less than j, vertex vj is not incident to edge ei. Okay, so is that right? Did I flip the signs around here? Yeah, I flipped this. I flipped this around here. Yeah, of course. This is not true, but this should be vi is not adjacent to ej, where ej comes later. Because remember, when I'm removing vi, I'm saying at this moment, it's only adjacent to edge ei, that one edge going out of it. It may be adjacent to the edges earlier that I removed, right? They may have gone to it, but it doesn't go, the only forward edge it goes to is when j equals I. But a later j it doesn't go to. Like, so here when I'm at v5, it's not adjacent to edge e12 at all because it's adjacent only to e5 at that step there, okay? So that observation says the following here, that now if I rewrite the matrix Q of S as follows, and now let's index it by v1, v2 up to vn minus 1. Sorry, there's no v1, but let's just, let's pretend it's there for a moment. I'll cross it out, but this matrix, this is Q of S, and then the edges here are actually e1 up to en minus 1. So it's an n minus 1 by n minus 1 matrix. Then what this represents, like, remember I talked about here, let me color this in red. Here was like a renaming of the vertices, right? Like there were vertices 1, 2, 3, 4 up to n minus 1. And now I gave them a name, n1 or vn1, v1 up to vn minus 1. And they did the same with the edges. What that's actually doing is that's just permuting rows and columns of this thing here so that I move supposed v1 up to the top. I actually move v2 up to the top, vn minus 1 up to the bottom, and so shift these around to follow that ordering, okay? So it's not a relabeling, it's just a shifting of the rows and columns. But this observation does something really nice. So v2, wait, what am I missing here? Something slightly off. Oh, yeah, okay, no, we're fine. v2, e1, I want a plus or minus 1 here. by the way, there's one other little mistake here. So that we do go down to Vn there. So I want this to be a lower triangular matrix, and it should be here, but let's see here. So V2, it's not clear that it should be plus or minus 1. To me, I see it's potentially 0. Okay, so one thing we can do immediately, this is part of it here. So this, the diagonal here is in green, that we'll worry about in a minute. What can you tell me about the upper part of this matrix here? Up here, should be.
That's all zeros.
Yeah, these are all zeros. That follows by this observation here, right? V2 is not adjacent to E3, E4, and so on and so forth, although it is adjacent to E2. Yeah. And then down here, we'll not know. And I want so if I delete the first row here, that is going to give me what I want, because V2 is definitely adjacent to E2, so it gets a plus or minus 1 and so on and so forth. But I think I did this indexing slightly wrong. Let me think here. So, and it would certainly work if I re-included V of 1, then I'd have this nice diagonal matrix, but I can't just magically do that because I'm not asking for the determinant of QS with the first row there. I've deleted that row. I don't have access to it when I'm actually doing a computation. We're actually, it seems like we'll finish just fine here. Let me take a quick look at a book here that has what I'm doing here, and then maybe I can solve it here. I'll have to fix this in the notes too. Okay, so yeah, it's not helping. Possibly, I need to do this enumeration, this procedure, like name things a little bit differently to solve this, but
Isn't there like, this is less precise, isn't there like a different approach that we can take? I mean, just sort of like, a lot of this reminds me kind of like when you look at like, like matroids, like we're looking at like, sort of like the similarity between like a cycle in a graph relates to a linearly dependent set of like, vectors.
Yes. Yeah, I mean, this actually is a motivator for the theory of matroids. It's not something we're going to cover in this class particularly, but yes, absolutely. So there's even there's more general approaches than we've done here. I've tried to slim it down on a few occasions intentionally. Let me think for a second here. Okay, so this essentially would be the end of the proof if we let me just state the things and then get back here. So if we actually got this upper triangular matrix that had all +1 -1s along the diagonal and zeros above, then the determinant of this matrix of Q of S would be plus or minus 1, right? It's just the product of the values on the diagonal. And then that implies what we actually care about is that the determinant of Q of S squared, that gets rid of a potential -1, gives us 1. And so the trees would indeed be counted once very nicely. So this would end the proof, but as of now, we're not getting the matrix that I desire. But let's think for a second here about what if we...
Is the issue that we're not getting an upper triangular matrix?
Precisely, Cameron. Yeah. So if you
the determinant be the same for a lower triangular matrix, or am I remembering?
Okay, that's a good point. But what I'm worried here about is the diagonal in this one could include zeros in the way that we've constructed it, right? Gotcha. V2, it may be adjacent to E1, but it might not be. Oh, wait a minute. No, not necessarily, right? Because let's think about the procedure here. I grab V1, and here's E1. right? And then I looked at the remaining graph here and found, oh, there's a vertex of degree 1 somewhere. Well, maybe it's here. Maybe there's V2, and here's E2. And then V2 was not adjacent to E1, and so this would actually be a 0. Because remember, this first row is missing there. If that row was there, then there would be a 1, or plus or minus 1, but not here.
Can we use that the trees have 2 leaves and then say, like, keep removing the same leaf? And like, you know, we have 2 leaves, so remove this one, then have this one, this one, this one.
Yeah.
Does that guarantee that our V1 is connected to E1, which is connected to E2 or to V2?
No, unfortunately not. Imagine the following tree, right? So like you could have this star here, and I'd keep having to remove these vertices down here one after another, but none of these are adjacent to any of the other edges there, right? So you can't get this, you can't get this nice backward sequence, which is what we want. It's possible a renaming here will work. Okay, so let's see here. There's 2 artifacts here that are troubling. So first of all, Vn, according to this procedure, will it have a 1 here? Shoot. I want to resolve this here. And really the only thing we have at our disposal is to fiddle with this enumeration a little bit. There are a few different things we can do. So
because we enumerate, like, one thing is like we enumerate the vertices up to Vn minus 1.
Yeah.
So like that V sub n
Yeah.
is like, maybe that's what we wanted to remove in the first place. Like maybe we wanted to label our vertices as V2 through Vn.
Yeah. Okay.
Incident on like edges like E sub 1 through En.
Let's try that. That's a good suggestion, Van. Let's try that real quick here. So let's say that we enumerate the vertices as V2 up to Vn. And then V1 is not enumerated here, which is okay. And V2 is adjacent. We give it the name. We name its edge E1, so the index is just like 1 less, right? This is just another way of going through this procedure. Remember, this is just a different naming of the vertices. And then in this case, this looks promising at least. We still have, okay, then this observation is slightly different. It says that if I is less than or equal to j, then vi is not incident to vj, because I is incident to I minus 1, but any forward one, you know, V2 is not adjacent to E2, right? And V2 is not adjacent to E3, and so on and so forth. And so then, let's ignore this first row entirely. Then V2 E1 is plus or minus 1. Remember, that depends on whether there's a plus or minus 1 in the corresponding, that end of that edge. So I can't actually predict that, but it doesn't matter. And then V3 E3 seems to be plus or minus 1. Yeah, I think we're okay here, Van. I think this works. And then Vn, yeah, will be En minus 1. So I'll get plus or minus 1 at the end here. There's all zeros up here as we specified. Down here, I have no idea. It depends on how the edges go back, but I don't need to know that. So it seems that this indexing will work just fine. Maybe we could have rewritten the whole argument where instead of dropping row 1, we drop row n, which was Vn or something, just to make it a little bit cleaner. But this seems to work just fine here. Just
yeah, that makes sense, because I think, again, then, like, pedantically, our observation, I think, only works for like index like I greater than 1, because like the thing is, like, which doesn't really matter because we were removing the first row anyways.
Right.
But
yeah, no, you're absolutely right. Yeah, moreover, I less than j didn't even make sense either when we reached Vn, although it was still held, but there was no n plus 1. Okay, so we just changed. Basically all we did was change the naming here of this. In fact, the old naming probably worked. Now that I think about it, if we additionally did appropriate row swaps after that, we didn't have quite what we wanted, but I think we knew there was a plus or minus 1 in the one next to the diagonal, and there was some funny business at the end, I think, with column swaps. We could have gotten it as well with the old one. Okay, all right. So I hope that's okay now. Just this slightly different renaming gives us this very nice matrix, and then the rest of this holds. The determinant is clearly plus or minus 1. It's just the product of the diagonals, and if you square it, you get 1. So that proves the theorem, right? We did what we claimed we would do, and that was this part here, that we would, each of the QS's corresponds to like a potential tree with n minus 1 edges. And we found that the determinant here contributed 1 if it was a tree and 0 otherwise. And each potential tree was counted here. So they all get counted once. So the determinant here, which is equal to this, counts every single tree once, and the non-trees are not counted. So that proves the theorem. And now let's apply it here in the last 4 minutes, because this is really pretty. So, because the nice thing about applying the theorem is you don't need to think about QS anymore. You just need to find the determinant of the Laplacian minus a row column, okay? So Cayley's formula says that number of spanning trees of Kn, right? We discussed that's the same thing as the number of labeled, like Kn with labeled vertices. It's the same thing as the number of labeled trees with labels 1 up to n, should be equal to the determinant of, not the complete graph, that doesn't make sense, but this reduced Laplacian of Kn. So let's try and determine that real quick. Let's look at L star Kn. I already described it earlier, but what does it look like here? So the Laplacian of Kn has n minus 1s along the row and column, along the diagonal, because those are the degrees of every vertex. If I remove the first, k minus 1, if I remove the first row and column, it looks the same, right? So n minus 1s all the way down here. And everywhere else we have negative 1s, because every vertex is adjacent to every other one, and so we put in a negative 1. And this one here, let's be careful. This is n minus 1 by n minus 1. The Laplacian is n by n, but we remove the first row and column, so we actually get this guy here, okay? So now, well, from here it's easy for you guys to find it out as well, but let's first step add all rows to row 1 and compute the resulting matrix. So if we add all the rows to, like this operation doesn't change the determinant, right? Adding rows. So we add all the rows to the first row, what happens? This n minus 1 gets n minus 2, the other rows, negative 1s added to it. So we get, I want to write 1. Did we get 1? We seems like we would get negative 1. No, we get 1. We have n minus 1 minus n minus 2. It's 1 bigger, so yeah. So we do have a 1 here. In fact, we also have 1s across the entire top, do we? Yeah. Because think about what, it's the same argument, but what happens to this negative 1 here? We add to it an n minus 1 and n minus 2 other negative 1s. And so, I'm sorry, n minus 3 other negative 1s. And so we get 1s. The whole top is 1s. And the remainder is the same, n minus 1, n minus 1, n minus 1. And what's not filled in here is negative 1s and negative 1s. If you get a row of all 1s, you're happy, because adding that and subtracting that from other rows, like multiples of it, you can do like almost everything you want. Because now let's add first row to all others. Same thing, we don't affect the determinant by doing that. If I add the all 1s row to every other row, all the negative 1s vanish, right? Everything's negative 1s, and these n minus 1s become n's. So, right, I have 1, 1 across 1, and now we have n all the way down to the end here, and then it's not even important, but these become zeros as well. And now we can figure the determinant of this. This is upper triangular, right? It's everything down here are zeros, and on the diagonal we have a 1 and then a bunch of n's. But remember, this was an n minus 1 by n minus 1 matrix. So how many of these n's do we actually have here? There's n minus 2 of them, right? The first one's a 1, the rest are n minus 1s. And that's great, because the determinant of this is equal to n raised to the n minus 2. That's Cayley's formula, right? So it's very, very simple, linear algebra there. Just some row and column additions there that gives you this guy. Once we have this like super black box, right? The matrix tree formulas, we proved it, but it's pretty non-intuitive, right? It's like, I can't look at the matrix tree and say, oh, that's sensible that counts the spanning trees. Like the steps weren't that hard, but they were like pure magic at the end of the day. So that proves the Cayley's formula from the matrix tree. But now we have this stronger tool that, for instance, I think problem 5 on the homework in principle can be solved using matrix tree. I haven't actually gone through the details. I know a few people have been working on that. You don't need to do it that way, but in principle, if I ask how many spanning trees are there of such and such graph, you could attempt to take the matrix of this reduced Laplacian and figure it out. So good. Okay, that'll do it for the day.